We can see the stars shining on the sky at night. But is it true that in space no one can hear you scream? The answer is yes. When there occurs a star explosion, the huge amount of light is released. The light, as it does not require a medium, travels and enter our eyes. But sound travels through the vibration of atoms and molecules in a medium. In space where there is no air, sound has no way to travel. Sound, the mechanical wave. That means it needs material medium to travel. Material medium means solid, liquid, or gas. Sound is produced by vibrating object. The vibrating object can be a drum skin, it can be a vocal cord, it can be the ruler which is pressed at one end and the other end is disturbed. A sound wave consists of mechanical vibration in air and other substances. And sound is a longitudinal wave, light transverse waves, but it is electromagnetic. In longitudinal waves, the energy travels in the same direction as the particle within the wave vibrate. Longitudinal wave, suppose this is the direction of propagation, that is towards right here, and vibration will be parallel or anti-parallel to the direction of propagation. So when there is no sound wave present, the air molecules move randomly. But when there is a source of sound present, like a speaker is turned on, alternate compressions and rarefactions are set up in the air. Compression, the region of increased pressure, and the rarefaction is the region of decreased pressure, where there are less number of molecules. Compression, where there is large number of molecules. Region of high density, compression, region of low density, rarefaction. And the wavelength of a sound wave is equal to the distance two between the center of two successive compression. So this is the wavelength from the center of one compression to the center of other compression. In the same way, we can take it from the center of one rarefaction to the center of next rarefaction. So how does the sound wave travel through the air? By means of the disturbance in the particle of the medium. And here the compression is set up where the molecules are more in number and the rarefaction where the molecules are less in number. So this compression and rarefaction, they pass on from atom to atom and the sound wave propagates. So here we can see the first layer, the first atom next to the speaker first passes on its oscillation to the neighboring one, and then this process goes on and the compression and rarefaction are set up in the air and the compression reaches the end. In the same way, the rarefaction. So sound is a wave and we measure the frequency of the sound in hertz. Frequency, number of waves in 1 second. So we can hear the sound in the range of 20 hertz to 20,000 hertz. 20 hertz means 20 vibrations in 1 second. 20,000 hertz means 20,000 vibrations in 1 second. Age and damage reduces the upper limit. Upper limit 20,000 hertz. Okay, like a person who is old and the person who has experienced some accident or he was exposed to prolonged high sound volume may not be able to hear above 10,000 hertz. Some animals here can hear much higher frequencies, like dolphins. They can hear up to 100,000 hertz. Bats can also hear up to 100,000 hertz. Dogs, 40,000 to 60,000 hertz, depending on the breed of the dogs. Ultrasound and infrasounds. Ultrasound is a high frequency sound above 20,000 hertz, too high to be heard by humans. Humans cannot hear it. Okay, so this is used in sonar, the technique to find out the depth of sea or ocean or the presence of underwater object, or in case of the presence of any stone in the kidney, that is for the scanning. Infrasound, a low frequency sound which is also inaudible to humans, although we may feel a very slow vibration, but we cannot. Earthquake waves are a form of infrasounds. Elephants and some other large animals can hear infrasounds. Sound waves in different materials. So they travel fastest in solid. A train can often be heard approaching through the rails before it can be heard through the air, because the rail is made up of steel, steel is solid, and sound travels faster through the solid. Okay, so we can hear the train approaching, and through the air we will hear it later. It can travel through liquids also. Whales can communicate over longer distance under the water due to this. Sound travels slowest through the gases. The speed of sound increases with the temperature. Sound does not travel through the vacuum as we just discussed earlier. It needs a material medium to travel. So you cannot be heard in space. Now, bell jar experiment to show that sound needs a material medium. Here, the jar is taken which is full of air in the beginning, and there is a bell inside. So when the bell is operated, the sound is heard and the bell is seen also. The ringing of the bell can be seen. We will see the hammer hitting the gong, and we will hear the sound as well when the air is present. But when we start decreasing the air in the jar by means of a pump, what happens? The pressure of the air inside the jar will reduce, and the loudness of the sound will also be reduced. And eventually, if the whole air is removed, no sound will be heard. But we can see the bell ringing because sound cannot travel through the vacuum, but light can. Reflection of sound. Echo is a reflected sound. When sound bounces off the surface, it is heard again. We call it echo. Now, there is a case to discuss or solve. A misguided child shouts, "Help!" at a nearby cliff and hears an echo 1.4 seconds later. How far away is the cliff? Take the speed of sound equals to 340 meter per second. So the sound is traveling towards the wall, towards the cliff, and it is returning. So distance, one way distance is d. So going towards the cliff and returning towards the child, the distance traveled is 2d. Speed is equal to distance over time, the famous equation. So distance is equal to speed multiplied by time. So 340 into 1.4, 476 meter, but it is 2d. So what will be d? D will be 476 divided by 2, that is 238 meters. Sound refracts also. Here a child A is shouting, and child B and C are standing close to him. So what happens? The child B hears sound more clearly compared to child C, because the colder air here will refract the sound towards the child B. So the child B at position B or person B will be hearing more clear sound. So cooler air over the water refracts the sound wave downwards. Measuring the speed of sound. So now this is the famous experiment using visible loud event. What is done in this experiment? Use a stopwatch to time the difference between seeing and hearing the event. For example, an explosion. Measure the distance between the event and the timing position. Speed is equal to distance upon time. The formula is to be used. And the distance should be as large as possible in order to avoid significant reaction time error in the timing measurement. Okay, so the distance should be large enough. Okay, when the gun is fired, on seeing the spark, the person will start the stopwatch, and when he hears the thunder explosion sound, he will stop the stopwatch. So here, this is the demonstration. The distance between the event taking place, that is where the gun is set up, position A, and the position of the person who is timing the event is B, and this distance is measured. So when the gun is fired, the stopwatch starts, and the stopwatch stops when the sound is heard. So that time interval will show the distance traveled by sound to travel from A to B. Now, a question. A group of students measured the time taken between seeing and hearing another student who is 25 to 50 meters away, clashing two pieces of wood together. They obtained the following timings in seconds. So the group of 5 students, so they got different ratings: 0.73, 0.78, 0.69, 0.81, and 0.77. So what is to be done to find out the speed of sound? The source is 250 meters away from the observers who are timing. So we have to calculate the average time here in this case. So what is the average of these 5 times? That is 3. We will add them up and divide by 5 because there are 5 observations taken. So 3.7578 divided by 5, 0.756 second is the time, average time. So speed is equal to distance upon time. Here we will write average time. So the answer is 330.69. So that is 331 when we express our answer in 3 significant figure, 331 meter per second. Measuring the speed of sound. Now using echoes, echo reflection of sound. So facing a flat vertical surface, it could be a wall or a cliff. At least 50 meter away, one person clashes two pieces of wood together. This person should try to clap the pieces of wood in time with the echo they hear coming back from the flat surface. So he has to practice, he has to take some trial reading, he has to first clash, produce two pieces of clash by hitting two pieces of wood together. This sound will go, it will be reflected from the cliff or wall and it will return. When the first echo is heard, the student has to clap along with that echo. That echo, the sound will again go travel towards the cliff and return, and the again the echo is heard, and the person has to take some trial reading of producing clash along with the returning sound. So that is how they would do it 20 times. Another person times 20 claps on a stopwatch. They should count 0, 1, 2, 3 up to 20. So measure the distance d between the clapping person and the flat surface. So clapping distance d, and sound goes towards the cliff and returns, that means distance is 2d, and it is done 20 times. So 20 into 2d. Speed is equal to total distance divided by time for 20 claps. So this is how we can calculate. In an experiment to measure the speed of sound by echo method, when a student stands 75 meters away from a wall, 20 claps are heard over a time of 8.77 seconds. Calculate the speed of sound. So total distance traveled by the sound. How do we calculate the total distance? Because it is done 20 times. Sound goes, comes back, means 2D. So 2 times 75, multiply by 2D, multiply by 20, because it is done 20 times for 20 claps. Sound goes and returns 20 times. So the total distance covered by sound is 3000 meters. Speed, total distance divided by time for 20 claps. So answer is 342 meter per second. Now the depth finding experiment. Here there is a CRO screen which shows the time interval of 0.5 seconds. Time is taken along x-axis and amplitude of the transmitted sound is along y-axis. So when the ship sends pulses at regular interval towards the bottom. So the pulse goes towards the bed of the sea or ocean and reflects from the bed or any underwater object, and it is received. When it is received, the received pulse is also shown. Transmitted and received pulses are shown on the CRO screen. So we can see it. So the time interval between transmitted pulse is longer in amplitude, of course, because it is sent by the ship, and the reflected pulse is lower in magnitude. Why it is lower in size? Why the amplitude of sound is the reflected pulse is less? Because the sound is absorbed while traveling towards the bed of the sea or ocean, and it releases its energy is decreased. Okay, this energy is transmitted to the surrounding water in the form of heat, etc. So, and then it goes and hits the bed of the sea or ocean. Some energy is absorbed over there, and then it reflects. So, while traveling back, that is towards the sea, towards the ship, the again some absorption occurs. So the amplitude of reflected sound or received pulse will be less than the amplitude of transmitted sound. So this technique is known as sonar, that is sound navigation and ranging. So we can find out the depth of underwater object, presence of underwater object like submarine, etc. Same technique is applied to find out any stone in the kidney using that ultrasound setup. Now, this is the calculation. Speed of ultrasound in water, 1500 meter per second, and then time interval between the transmitted and reflected pulse is received at 2 seconds, and the pulse was transmitted at 0.5 seconds. So what is the time interval? 2 minus 0.5 is 1.5. So the time taken by ultrasound to travel to the bed of the sea or ocean and return is 1.5 seconds. Speed is equal to 2d over time. Why 2d? Because sound goes towards the bottom and returns. So 2d over t, 1500 is equal to 2d over 1.5. The time interval, time taken by pulse to go and return. So the distance is 1125 meters. Speed of sound examples. So in different materials, air at 0 degrees Celsius, the speed of sound is 330. At 20 degrees Celsius, the sound will be traveling faster, that is 342. Air at minus 10 degrees Celsius, 325. Fresh water at 25 degrees Celsius, 1497, almost 1500. Sea water at 25 degrees Celsius, 1560. Steel at 20 degrees Celsius, 5000. And vacuum, 0. Sound cannot travel through vacuum. No one can hear you scream in space. Thunder and lightning. So when this occurs, light reaches the observer in 16 millisecond, 16 millions of a second. The sound of the thunder reaches the observer in about 15 seconds. An observer 3 miles away sees a lightning flash about 15 seconds before hearing the thunder. Every 5 seconds difference equates to a distance of 1 mile. Now the calculations. A thunderclap is heard 12 seconds after a lightning flash. Calculate the distance to the lightning flash Take the speed of sound 340 meter per second. So speed is equal to distance over time. So distance, speed over time is laid. Now characteristics of sound. Loudness. Loudness of a sound increases with the amplitude of the sound wave. It also depends on the distance from between the source and the observer, and area of the sounding body as well. So this is a quiet sound and this is louder sound. The higher amplitude means louder sound. The other characteristic is pitch. The pitch of a musical note increases with frequency. So the higher the frequency, the greater the pitch. So this is low pitch and this is high pitched. More frequency means high pitched. Quality or timbre. Quality or timbre is of a musical note is what makes one musical instrument sound different from another, even if they have the same fundamental frequency. So the different instruments, the sound they produce will be different in shape. So timbre, let us see the detailed view of it. Tuning fork, it produces sound of pure note. Pure note means single frequency. No other frequency is added. But all other instruments, musical instrument, including the human being, we don't only speak with single frequency, we speak with the multiples of our fundamental. Fundamental is the lowest frequency with uh, which a person can speak with. Like flute, this may be the waveform of a flute. It has 3 or more frequencies added to it. So the waveform is different. Voice of a person, it may look like this. Violin may look like this. So the waveform is different even if the fundamental frequency is same. So we can identify which musical instrument is being operated. Question here. The diagram opposite shows the appearance of a sound on an oscilloscope. Draw a second diagram showing the appearance of a sound wave which has the lower pitch but greater loudness. So what will be drawn here? Greater pitch, lower pitch means low frequency and louder means higher amplitude. So this will be the waveform of the wave which is to be drawn here. So that's all for the today's video. So we will see each other in the next video. Allah Hafiz.